So I'm going to start up on problems that came out of 6.1, section 6.1. So I know that I've kind of been slow with these videos, but um, I'm going to start picking up the pace, hopefully pick up the pace so I can get through chapter 6 for the most part. So before I get into problems, I've chosen 6 problems from page 298 of section 6.1. 3 of them are odd, so those will be done based on the homework that was assigned to you. And then the other 3 are even, and I want to discuss those. But before I do that, I want to bring up a formula that came from your book. So I took a look at the section after I did my summary, which took about 20 minutes the last time, the 6.1 summary. So I want to just summarize this antiderivative, and I hate that it's here because there's a different way that you would normally do this integration. It's normally called the substitution rule because you have to compensate for the chain rule that you learned in differentiation. So now you have an opposite way for the chain rule when it comes to integration. So it's this chain rule compensation called substitution rule is not in chapter 6. You'll probably learn it later, but they just gave a general note of what this antiderivative is. So I'll just go right into it. It's 1 over k e to the kx plus c, and k cannot be 0. If you have 0, then you actually have a constant, and then that derivative, the antiderivative is c, a constant, from the last section. So let's use as an example, let's say e to the negative 2x dx. So the k is negative 2. So in this case, I have negative 1/2, right? Because k is equal to negative 2. E to the negative 2x plus c. Right? So that's 1. And then let's say e to the 5x dx. So k is equal to 5. So in this case, it's 1/5 e to the 5x plus c. Right? So I wanted to bring that up, but I hate that it's here, just like I said before, because there's other ways to do this problem. So right now, unfortunately, let's just talk about using the formula as the book is designated, and then you'll get into how that comes about when you talk about the substitution rule. So the 6 problems that I've chosen from page 298, I chose number 2, number 12, number 15, 18, 21, and 24. So I'll start with number 2. It says find the antiderivative of f of x is equal to 9x to the 8th. So we know from the summary that asking this question or making this statement to find the antiderivative is the same thing as saying this. The integral of 9x to the 8th dx. So let's use a property. So I'll pull the 9 out, and now I just have the integral of x to the 8th dx. So using the power rule, I'm going to have 9 times. So remember, we raise a power, or we add 1 to the power, so I have x to the 9th. So 9 is 9 over 1. Take the reciprocal, so flip the fraction. So it's 1 over 9 and place that right in front. Plus c. So now it's just the simple math of 9 times 1/9. That becomes 1. So I'm left with x to the 9th plus c. And that's your answer. And the way that you can check this, remember we talked about antiderivatives. So this right here is the big F, right? And this one is the little f. So all I have to do is take the derivative of big F, and hopefully it becomes little f. So if I take the derivative of x to the 9th, pretty quick in the mental math category, we know that the derivative of x to the 9th is 9 to the 8th. So of course that's going to work out for us. So yeah, that's correct. All right. So now we'll go to number 12. So this one is x times x squared dx. So in this case, there were no rules that we discussed talked about the product of two functions within the integral. So when that is the case, we have to simplify this, right? So we have to simplify. So going back to your property of exponents or your laws of exponents, you know that if two exponents are being multiplied together and they have the same base, all you have to do is add the exponents, right? Or add the powers, right? So in this case, I have an understood 1 and then a 2. So what I really have is the antiderivative of x to the third, or find the antiderivative of x to the third. So it's the integral of x to the third dx. So we've discussed this one fairly quickly and fairly simple. From the summary, I'm going to add a power to the x cubed. So 3 plus 1 is 4. 4 over 1 is the exponent. So flip it. And now I have 1/4. That 1/4 goes in front of the x plus c, and you're done. So if you actually take the derivative of this, you're going to come back to x thirds, so that one's a good one too. I also chose number 15. Let's see, what's that one? 15 is the integral of x times the square root of x dx. So again, this is another multiplication of two functions. One is the square root function, the other one is just the linear function, x. But we know that the square root function actually has an exponent. It's a fractional exponent. So what I'm going to do is I'm going to simplify this even further and say that I have x to the first, because when the power is not there, it's understood as 1. But I'm going to change the square root to x to the 1/2 power dx. That's exactly what the square root function is. It's x to the 1/2 power. So again, same basis, add the exponents based on the law of exponents, and I actually have x 2/2 is 1, and x to the 1/2 dx, and then that gives me x to the 3/2 power dx. So I'm going to add 1 to 3/2. So 3/2 plus 1 is 3/2 plus 2/2. That's 5/2. So that's my that's my fractional exponent. So I'm going to flip it and throw it in front of the x, and I get 2/5 x to the 5/2 plus c. So if you took the derivative of that, you would actually get back this one, x to the 3/2, which is actually the expression, this algebraic expression of x times the square root of x. So that one's a good one. So another one that I've done was, okay, I did number 18. So this one is the integral of 7 over 2x cubed minus the cubed root of x dx. So I have a few properties here that I want to take care of, and the first thing that I want to do is break up the subtraction with the integrals. So I have 7 over 2x cubed dx minus the cubed root of 3. I'm sorry, the cubed root of x, sorry, dx. And now let's simplify this a little bit more. Well, for the first integral right here, I'm going to pull out the 7/2 because that's the constant or the number that's in front of the function, which is 1 over x to the third. And I'm going to have 1 over x to the third dx. So that 3 is really the root, not the coefficient, right? So be sure to realize that it's the root, not the coefficient. So there's no 3 that I'm pulling out. But what I do want to do is I want to express this cubed root as an actual fractional exponent. So that's going to be x to the 1/3 dx. So I'm going to simplify this a little bit more because now I know that because it's 1 over x to the third, it's the same thing as saying 7/2 times x to the negative third dx minus x to the 1/3 dx. So right now all I was doing was simplifying and making it easy for me to integrate. So right now I have 7 halves, make that a 7. And now let's take care of the integration. So I have -3 plus 1, that gives me -2. So I have x to the -2. And remember, -2 is -2 over 1. So if I flip it, it's going to be -1/2. Right? I'm going to take care of the plus c at the end because I have another one. Minus, so now I have 1/3 plus 3/3, which is 1. 3 over 3 is 1. So now I have x to the 4/3. That's my power. So flip it and throw it in front of the x. I have 3/4 plus c. So let's simplify it a little bit. So I actually get 7 times -1 is -7 over 4 x to the -2 minus 3/4 x to the 4/3 plus c. I wouldn't go crazy with simplifying this anymore. I would leave it just the way that it is. If you took the derivative of this, you would come back to a derivation of this function right here, this difference. Another one that I chose was e, and that's the antiderivative of e with respect to x. So the integral of e dx. So let's remember that e is a constant. So e is equal to 2.818, goes on forever. It's a non-terminating decimal. So because e stands for a number, it's the same thing as saying having 2.818 right here. Well, if I just have a constant inside the integral, then all I'm going to do is add an x. And that's your integral. I mean, that's your antiderivative. E times x plus c. So that one's good. And then the last one that we have, I chose number 24. So that's -3e to the -x plus 2x minus e to the 5x over 2 dx. So what I want to do is I want to break up and pull out constants for multiplication. So ultimately I'm going to do this first. So I'm going to do the -3e to the -x dx plus the integral of 2x dx, because all I'm doing is breaking it up now, minus the integral of e to the 5x over 2 dx. So now what I want to do is I want to pull the constants out that are in front of the functions. So in this case I have -3 e to the -x dx plus 2x dx minus 1/2 integral e to the 5x dx. So all those are working in our favor by pulling them out so that we have easy integration. So using that formula, remember it was e to the kx, or the integral e to the kx dx, that's equal to 1 over k e to the kx plus c. So in this case, my k is -1, so I have 1 over -1, which is -1, e to the -x. I'm going to put the plus c all the way at the end, because at some point I know I'm going to have to get that constant. Plus 2 times, so x to the first, add 1 to the x, so I have x squared. 2 over 1 is the actual fraction. Flip it, it's 1/2. Minus 1/2 times, again, in this case, k is equal to 5. So I have, based on that formula, 1 over 5 e to the 5x. And now I'm going to add the plus c. So ultimately, I need to do all of my simplification and do all my multiplication. And I get Negative 3 times negative 1, that's positive 3 e to the negative x. I have 2 times 1/2, that's plus 1, so that's x squared. And then I have negative 1/2 times 1/5, that's going to be minus 1/10 e to the 5x plus c. And you're done. So these are the 6 examples that I chose, and hopefully these give you a really good understanding of completing all your homework, doing all those odd problems that you were given. And if you have any questions, again, hit me up, Messenger, FaceTime, whatever you need to do. And if you like it, say so. If you don't like it, say so. And I will talk to you later, and we'll start up with section 6.2, where we talk about definite integrals and the net change.